First of all, I would like to thank for the invitation. It's a great pleasure for me to be back to Pittsburgh. Last time when I was here, it was sunny, so it proves that it's sunny sometimes in Pittsburgh. So today I'm gonna talk about my recent research that was devoted to the question of whether it's possible to have persistent symmetry breaking at any arbitrary temperature. And the answer to this question is yes. We managed to find a lot of interesting models, quantum field theory models, classical spin models, where symmetry breaking is present at arbitrarily high temperature and even an infinite temperature. We managed to publish 2 papers on that. You can find all of these models in these 2 papers that were written together with Dr. Komargodski, Andy Lucas, and 2 of Andy's students, Vicky Han and Xiaoyang Huang. And we managed to see that there is some general principle behind all of these models that allows to have persistent symmetry breaking at high temperature. And such principle or mechanism we decided to dub as entropic order. So the main aim of my talk is to explain to you what is an entropic order. So let me start with reminding what is the classical argument why we expect that symmetry must be present at high temperatures. I tried to find the first appearance of this argument in papers, and I think it was given by this paper by Landau, where he introduced the theory of the quantum phase transitions. So the classical argument goes as follows. Assume that you have some theory that has C2 symmetry. For instance, it could be scalar field theory with symmetric potential drawn here. Then if I want to compute some correlation function or some observable, I just need to compute this integral that we all know from high school physics. So just integrate all possible states, take into account density of states and Boltzmann probability factors. And after that, we just need to compute what happens at different temperatures. If temperature is low, the Boltzmann factor dominates, and the system, the theory, will try to stay around one of the vacuums. Of course, it can tunnel to another vacuum, but if this hill is quite high enough, then these fluctuations will be suppressed, and this transition could happen, but after a very long time. So we will notice only the system lives around this vacuum state, and we will see symmetry break. At high temperatures, this Boltzmann factor ceases to be important, and the system tries to maximize entropy. So it will try to spend equal amount of time at each of the states, and will have restoration of the symmetry. So it's a simple argument, and it seems to well align with our everyday experience. We know that water, ice melts, superconductor ceases to be superconductor in some temperature, magnets cease to be magnetic when you heat them up. So maybe it's correct. But after that, you can find a lot of interesting examples in nature that contradicts this logic. The most simple one is Rochelle salt. It's not some very weird material. You can just go to Amazon and order it. I took this picture from Amazon. And it has an interesting property that as copper at low temperature, it exhibits spontaneous magnetization. But actually, it exhibits spontaneous magnetization around 0 Celsius. So the system, this material has 2 Curie points. At low temperatures, it does not magnetize, but around 0 Celsius, it exhibits this spontaneous magnetization. But miracle does not happen. This spontaneous magnetization ceases to exist at some very high temperature. And actually, this Rochelle salt discovery of this interesting phenomenon motivated first Steven Weinberg to find such quantum field theories that would have such interesting behavior. And the other example that is much more relevant to the topic of this talk is so-called Penderanchuk effect. For that, you take helium-3, now you cannot buy it on Amazon, put it under high pressure, 10 to the 5 atmospheres, and after that, study phase diagram of this material. And you find out that at low temperatures, it exists in a liquid state. At high temperature, it exists in solid phase, so like usual water, but the latent heat of this phase transition is negative. So it means that if you put these ice cubes of helium-3 into your beverage, it instead of cooling down, it will heat it up. So for this purpose, it's completely useless. But if you want to reach very low temperatures, it absorbs energy when we will cool down, that allowing us to reach very low temperatures. So it was very big mystery why it's happening, and apparently Pomeranchuk managed to explain to it. I took the spot from his paper that we can find here And he says that entropy of the solid phase is higher than the entropy of the liquid state. And he explains that by stating that a solid phase has some vibrational modes. And because of this vibrational modes, the entropy of the solid phase is higher than of the liquid state. And he made some estimations that considered well this experimental observation. Now it's named as a Pomeranchuk effect. It's widely used in experimental physics techniques. Okay, so maybe our semi-qualitative argument was incorrect. So let's try to make it much more rigorous. For that, let us ask some people who like rigor, so mathematicians. And apparently there is a theorem that states that if you have some specific systems, then you must have restoration of symmetry breaking at very high temperatures. The theorem is called Dobrushin theorem or Gibbs uniqueness theorem. You can find this theorem here. And it states the following. Assume that you have a classical spinor system and assume that locally, so if you cut out a sublattice from your model, it has a maximally mixed state, just identity state. It just means that it has a finite number of states. And then if you impose boundary conditions infinity, and not infinity, it's a border of this lattice, and takes this lattice to infinity, then first of all, the Gibbs state could be expanded like that. And this expansion is analytic and calls for t bigger than some number t star that uniform only depends on parameter of the system. And this expansion does not depend on the boundary conditions. You might think it's some very complicated theorem, but actually it's a very simple theorem. It's just like very pedestrian way to do high temperature expansion. Like for instance, in Ising model, we usually expand factors coming into energy like that and do such a loop expansion. And after that, you just do some very careful estimations and shows that this large temperature expansion hold and analytic for t bigger than t star. And from that, you can immediately prove that spontaneous symmetry breaking must not be present at very high temperatures. Indeed, let us compute the vacuum expectation value of some operator phi that is odd under this C2 symmetry for t bigger than t star. Then using Dobrushin theorem, I can state that this average was computed with some boundary condition at infinity, say plus. After that, I can flip all signs and get that boundary condition states that spin must be -1, and I get here additional sign. But again, I use the Dobrushin theorem and replace this minus with just usual average. So phi must be equal to -5, hence it must be equal to B0. So you might assume that from that I can end my talk earlier, and it just can go home. But there was a very big assumption about that locally there exists only finite number of states, and there exists infinite number of states locally. Then this high temperature expansion would not hold immediately. For instance, here you will immediately get infinities. So maybe if we introduce some Bosonian degrees of freedom on the lattice, we will get spontaneous symmetry breaking that persists at very high temperatures. So let me just show you that it's indeed happening. For that, let me consider again Ising model. So we take some lattice. At each side there exist spin variables that equal plus -1. But now along each link we add some additional bosonic variable Nij. So it looks like lattice gauge theory, but it's a little bit different. And this bosonic degree of freedom goes from 0 to plus infinity and controls the interaction between these two spins. So the Hamiltonian could be written like that. So at first glance, it seems to be a very complicating Hamiltonian, but nevertheless, we can integrate out bosonic degrees of freedom here and get that the actual effective Hamiltonian describing interaction of spins is again has the form of Ising model, but now the effective temperature that appears in the Hamiltonian is different from the actual temperature that we set by the thermostat. It's some complicated function of these parameters A, B, and T. But interesting property of this function that one can show that this temperature is bounded from above by this combination. And hence, I can fine-tune my parameters in such a way that this number will be less than the number of the critical temperature. And hence, my system, my spin subsystem will never feel very high temperatures. It will feel only low temperatures, and hence the spins will always be in the ordered state. Yes?
The notion of effective Hamiltonian, I mean, I just have to follow the temperature implies that we consider the exponent of Hamiltonian
Yes.
the temperature, right? Then summing up over.
You can do here exactly.
Yeah, so like why the answer will be still described by some Hamiltonian, you know.
Local, like Isaac model. It happens because of each individual sum, Nij. Here, I forgot to put here. You can individually sum this Nij, and it always will be in the same form like Isaac model. So it just happens because of sigma I, sigma j, this product takes two values, plus 1 and minus 1. And so when I went sum this infinite okay. And so I can set up this number in such a way that it will be always lower than the critical temperature, and hence my spin system will always be in the ordered state. What physically is happening is that this bosonic degrees of freedom, they prefer sigma I, sigma j to be correlated. Because of when sigma I, sigma j are correlated, the effective chemical potential for each of these mu is less than sigma I, sigma j disordered. And hence we have more entropy when they are correlated rather than when they are disordered state. And small remark, you might think that maybe if I put here some big number m, maybe this still holds, but actually not. One can show that this function now is not bounded from above. It goes from 0 to plus infinity, and hence still at this like bosonic but finite Isaac model, we would have a phase transition, but at very high temperature. So here we need to take in the limits that n goes from 0 to plus infinity. Okay, so now let me give yes.
Things like UI instead of R, which you are the
Yes.
this was very better.
For gauge fields, there is a little bit more complications that you cannot directly apply this Dobrushin theorem because if you cannot simply cut it out the sublattice. It reminds lattice gauge theory, but it's not.
But normally, you would think that this LW below the temperature, when you are saying that here you are ordered state, right?
Yes, ordered state.
So normally, I would think that LW will be less than.
Yes, yes, but as in the case of Paper-Anchuk effect, ordered state has more entropy, and here it's again the ordered state has more entropy.
I think that there is kind of a total contradiction. If it's ordered, who creates it? Because more entropy, not kind of sounds as a.
No, okay, let me. I will give you another model where you can immediately see that the ordered state has more entropy. We'll just compute it. Okay, so let us consider another model because of. So we saw some strange, I think, model with some additional bosonic degrees of freedom. Now it will contain only bosonic degrees of freedom, and hopefully this model could be actually realized on some photonic processors. So for that, we will take lattice gas model that was first introduced in this paper that we have heard a lot about it. It's the same paper that introduced Lee-Yang H singularity and all of these ideas about PT-symmetric Hamiltonians. So this lattice gas model is just an anti-fragmented Ising model in disguise, where we just replace our sigma variables -1 and 1 to 0 and 1, and just study the full Hamiltonian. At low temperature, it exists in solid phase or checkerboard state, like here. At high temperature, it goes to the Gaussian states that I tried to depict here. It obeys Dobrushin theorem, and for low temperatures in the ordered state, that breaks Z2 symmetry, that breaks shift symmetries. And at high temperatures, the symmetry is restored. So the translational symmetry gets restored here. So now let's try to play the same game and say that these numbers and I are not binary, but take values in all positive integer numbers going from 0 to infinity. And for the reason I explained in the next slide, I will say that this interaction is not quadratic, but have some polynomial form. And also I will change the sign of this interaction U to plus U. I need that to have a sensible model. If there was minus sign, I would have infinite number of states in any given energy range. With plus sign, it has a finite number of states in any given finite energy range. So now, as we learned yesterday, let's ask computers what's going on in these models. So the top two slides videos are simulations for A is equal to 2. We see that for high temperatures, this model goes to the ordered state. For low temperatures, it exists in the gas state. And let's try to explain why it's happening. For that, I will compute the partition function of the checkerboard phase and gas state at high temperatures. It could be very easily done. In the checkerboard state, we have just L squared over 2 occupied lattices. So each yellow cell corresponds that there is some number of particles in it. Black line corresponds that there is 0 number of them. At each, since there is no interaction between lattices, the only effects that you should take into account is chemical potential. Could be easily taken into account is also the temperature. It has the partition function of free energy is behaves like T to the power L squared over 2. If we compute the same thing for the gas phase, we need to take into account interaction between two adjacent cells, and we need to set the following cutoff, that n should be less than T to the power 1 over 2a. And doing the same estimation, we see the partition function Z gets a contribution for the gas phase of the order T to the power L squared over 2a. And if a is more than 1, then for high enough temperature, checkerboard phase will dominate over gas phase. And that's what we see here. Now the question is about a is equal to 1, because of now this contribution coincide to each other. First, we thought that actually it always will exist in the gaseous state, and we did some Monte Carlo simulation and always got that the picture looked always like that. But after that, we managed to improve our code. We managed to launch it on much better computers and waited for long enough and see that eventually, after some long time, it still goes to this ordered state at very high temperatures. And why we are interested about this A is equal to 1 is because of this particular model we believe could be realized on some photonic processors, where I is just some represents the occupation number of photons at each cell of this photonic processor. Okay, so and again here we see that ordered this high temperature ordered state happens not because of energetic reasons, but because of entropic reasons. That entropy of the ordered state here is higher than the entropy of the disordered state. Okay, so now I shared myself more with HPH community, so let us try to find some quantum field theory models that also exhibit such interesting behavior. For that, actually this model has already been studied, but they were studied in 4 minus epsilon dimensions by Zohar Komargotsky, Misha Smolkin, and Elizabeth Rabinovich. They managed to show that there exists persistent symmetry breaking at a very high temperature, but the main complaint was that it existed in 4 minus epsilon dimensions. So it might be the case that such a phase does not exist, such a property does not exist at integer dimensions. So with that, we try to do the same computation, but in 3 dimensions. But now we try to use large N computations. So the model I would like to consider is the following. We have just a critical ON model depicted here, and we add a free scalar field on top of this system, and we make introduce some interaction between these two subsystems. Such ways that ON symmetry is preserved. And also, in 3 dimensions, we should take into account that there is also relevant perturbation created by the field psi itself. Now, the leading order in N, this coupling is marginal and can be set to any value. But since we want to see something that happened not as an artifact of the large N limit, we should take into account one of N corrections. And after some sort of computation, we managed to find the beta function for this value T. That's quite simple. And for the beta function for this coupling G, that was much more harder and it's much more bigger, so I will not write it here. But what you find out is that there exist 3 interesting points where T is equal to -1, 0, and 1. The first choice corresponds that psi decided to be aligned with yi, and instead of ON critical model, we get ON plus 1 critical model, and one controls that G in this case goes to 0. There is another interesting point when T is equal to 0. Then it's just like non-interacting critical ON model with a free scalar field, so it's not so interesting. But much more interesting happening when we take into account t is equal to -1. Then here we have minus sign, and one can show that G also becomes positive. This has some drastic consequences. For instance, now sigma cannot get condensed. For instance, if you study this critical line model at finite temperature, you'll see that sigma can condense and fields phi I becomes massive. But here, because of we have here a negative sign, sigma cannot get condensed. Because of this, either will lead to condensation of psi or phi. We must set sigma to be 0. And indeed, if we find the solution of this model at is equal to 1, we'll find out that psi must get condensed. This is not one-point function of psi squared operator. This is square of one-point function of psi. And we see from that psi must get condensed at very high temperatures. And to say that it is not some artifact of the large limit, people managed to do some simulation of this model using functional renormalization group, and managed to show that for n bigger than 15, this model indeed exhibits the spatial symmetry breakings at present at all temperatures. See here that dependence is very simple on temperature. It happens at all temperatures. Okay, so let me try to connect to this paradigm that we try to tell you, as that this persistent symmetry breaking happens because of entropic reasons. For that, let me compute the entropy as a function of energy in this model. It's very simple computation in the large limit. You just compute free energy as a function of the condensate psi, temperature T, and this parameter sigma. And after that, you can find entropy as a function of energy and the function of this condensate psi. And you will see that entropy of ordered state is always bigger than the entropy of the disordered state. Hence, if I will use some microcanonical description and just take some random state at some energy level, most likely I will get ordered states and ordered state. So we see again it's similar to the Pomeranchuk effect and to this lattice boson gas, and to Rochelle solves that again we get this entropic order. And the last but not least, let me talk about understanding towards high temperature superconductivity, even though it's different science collaboration. So let me try to find if it is possible to break U1 symmetry at any arbitrarily high temperature. In 3 dimensions, it would not be impossible. We still have the Coleman-Mermin-Wagner theorem that forbids that. But in 4 dimensions, we might play the same game and get the condensation of some field site and breaking of U1 symmetry that would be temperature resistant. So we play the same game. We introduce large number of fields Fii. We introduce complete scalar field psi and couple it to some gauge field mu. After that, using the usual large techniques, we can find the effective action describing this theory. And we find that at non-zero temperature, we must only have condensate of psi. But now we have a problem that the theory is not UV complete. So we cannot trust this result to arbitrarily high temperature. But nonetheless, it shows maybe still we can somehow break U1 symmetry, or at least somehow increase this critical temperature of this phase transition. Okay, so it brings me to the end of my talk. So I hope that I managed to explain to you that symmetry breaking is possible even at high temperatures. That reason for that is so-called entropic order, and this is a general phenomenon that people knew for quite a long time. That sometimes mathematical tools and numerical methods can lead us to uncover this fascinating phenomena, and the quantum series also supports this persistent order. And since I'm the last speaker, so let me thank everyone for very interesting and inspiring talks and panel discussions. I got a lot of interesting ideas. And thank you, Igor, Ricardo, Brisha, and Yuan for organizing this excellent workshop. Thank you for your attention.
Thank you much for this talk. Questions?
Yeah.
Your next study and also all the gauge field there.
It's not from this gauge field, it's just the stereo is not UV complete, so.
No. Yeah. We have a gauge theory.
Yes,
And, what's the interpretation of the gauge field play a role in this?
no, it's because of the other one,
Okay, so you're saying it's.
it's just suppressing the origin limit.
Okay, completely about.
Yes, exactly.
Yeah, but it's still, you're gonna limit yourself and.
Not some.
No, Model is from Harvard, right, so you should not go there anyway.
No, yes, but still, like, I cannot now claim that it goes to infinite temperature.
No, but once you put, that your organization point starts below, consider below.
No, yes, exactly, but now, but like in comparison to this one, where it's present at any infinite temperature, here we have still some cutoff. Okay, yes.
So this, bosonic model, you did, yes, for table one maybe, so. If I understand correctly, the key way this works, because with bosonic variables, the Hilbert space is open in the.
Yes, at each link,
When you put the temperature and you observe this, entropic order, what is the typical, occupation number on each side?
1 over beta,
So it's fine.
it's fine, yes. So like, if it was infinite, we would see some other color.
But if you calculate not the mean value, but the variance, higher moments, those will at some point.
I don't think so, just like, I think it will be fine. Fine,
I'm struggling with that. Somehow we will say that Hilbert space is fine. So you allow, let's say, 100 bosons on one side, but not more. Then the theorem which you mentioned at the beginning will preclude.
yes,
Somehow should be able to. Somehow this model secretly is putting infinite number of bosons on one side.
yes.
No, it is a.
Yes, I think what would happen is that now I would have a cap here, that for T, say, more than 100, instead of T, it's 100 here. And after that, also here, this all estimation will not go through anymore.
You're saying that finite Hilbert space can give the proper order of discernment that.
Yes.
If I want to continue temperature up and up, then.
Yes, exactly. Like here, if you cut off it here, finite number n, you'll see these functions now not bounded from above, just goes from 0 to plus infinity. So it happens only strictly in this large n limit. Sorry?
Then some doesn't compare that one for it.
It goes from 0 to infinity.
Yeah, but it's not. One that thing to be forced to say that one.
Oh, you say that, okay, maybe I made, yeah, I think I made my mistake in the class.
More questions? If not, let's thank Fedor again.